think if I were you, I would have swooped the first side and then swooped the other side. But yeah. This is also known as, I think, a cubed root function. Is that what you were switching? Was it a cubed root function? Or maybe it was just a picture. It might have just been a picture. We got number 26. It was another verify. And this one was weird because if you guys notice, they're the exact same function. Like, what's going on? They're the exact same. But when you plugged it in, didn't you realize the reciprocal of 1 over x is just x? And the reciprocal of 1 over x is just x? They're inverses of each other. And if you graph it, what do you notice if you graph the y equals x line? It's its own reflection. It's its own inverse and it's its own reflection. Huh. Okay, weird but true. 42 was a fail. You could have just said it's a quadratic. Of course it fails the horizontal line test. AKA the function is, the original equation is a function, but it's not invertible. It's not invertible. Number 52 has an A and a B and a C. And a D. If you guys noticed, once again, it was its own inverse. And once again, if you graphed it, it was its own reflection. Super weird. If you look at them, domains and ranges. Forever left, forever right, forever down, forever up, but the only thing that's not allowed for x or y is 0. So x can't equal 0 and y can't equal 0. Number 64, check it. Did you get plus or minus? Did you get plus, I should say, and minus? In solving, you should have square rooted, gotten an absolute value, which would have moved the plus or minus, and then we would have got to say it's not invertible. It doesn't have an inverse function. I can show you the inverse relation. I can show you the inverse as two functions. But I cannot show you f inverse of x because it fails the function test. Oh, and that was it? Oh, there we go. All right, guys. Where do we have questions? I'm ready. Yeah, 73. Anything else besides 73? No. Yeah. 14. Let me see. Oh, 14. Let me guess. Did you switch x and y, solve for y, and see that it matches? Yeah. Technically, what you did was indirect proof, in that you went outside of the problem, solved it yourself, and said, hey, it works. But when they technically say verify, you're supposed to go back to the definition and show that they undo each other. So it's not that you did it wrong, it's just you didn't realize what they were asking. So when they say verify or prove that two functions are inverses, they're giving you the answer like it's already been solved. They want you to show that they truly undo, which we can only show by does that make sense? Don't get lost. Just put your phone on your desk if it's in your pocket. Anything else besides 73 that we're coming to, then 14 that we just talked about? That's an odd two. Okay, let me start with 69 and 73, and then if anybody else has anything, there'll be one last call. So, let's do 69 just because it comes first. You were supposed to be finding the inverse. So if you guys noticed, I kind of don't like these directions. Because some of you, because of the directions, might have kind of made some mistakes, or at least not done what the book would have done. Because what's technically the first thing it asks for? Yeah, whether it has an inverse function. So what if you knew, like on, I don't know, where's the quadratic one? Here you go. What if you knew it was a no? Did some of you guys just stop and say, huh, it's a no? Moving on. Like, the directions kind of make it sound that way, right? Does it have an inverse? And you're like, no. All right, cool. Keep going. If so. But if you notice, didn't we grade one of these? Was it 64? I think. So you would have said no and stopped. But what did the book do? It switched it. It solved for it, and then it said no. Why did it do that? Some of these you can tell right away. Fails the horizontal line test. No. But others of them you can't, and so the safest way is to always switch the x and y, solve for y, and then say. So I don't like why they put it in that order. I think it's kind of messy. It's kind of misleading. So I apologize. And if you guys did say no and stop, it's not bad. But you should know that if you were to switch the x and y, there should have been a plus or minus that tells you no. But let's go to 69, right, Griffin? Okay. On number 69 down here, let me just get it alone so we can kind of focus on it. it gives us f of x, or y, equals the square root of 2x plus 3. Some of you guys might have been amazing and like thought of the radical function, square root of x, as the parent function. Does the radical function seem to pass the horizontal line? Yeah. So right away, maybe just by thinking of the parent function, you guys said yes, so we have to do the problem. But remember, I would have said just start anyway. So x equals the square root of, how did you guys start getting y of them? Yeah, square both sides. And the nice thing is there's nothing tricky with squaring a square root. There's no nasty absolute values that happen. We're able just to do the simple square root squared. So we end up with x squared is equal to 2y plus 3. And now it's just algebra as far as peeling away each of the operations done. So peel away the addition by subtracting first, and then peel away the multiplication by division. Technically, you're totally right if you write x squared minus 3, but in so many, all divided by 2. But in so many different places in math, it's going to be so helpful for you guys to realize that's the same thing as, careful, we're supposed to write it in our snazzy notation. 1/2 x times x squared minus 3. You guys realize that, right? Dividing by 2 is the same thing as multiplying by 1/2. Are we good? So technically, this top one would have been fine as long as you would have named him the inverse function, because he is no weird plus or minuses. That's okay, but that's another variation. And then technically, you could have also distributed. What did the book do? Did he leave it as a division? Did he leave it as a factored multiplication, or did they distribute? They distributed. Okay. But that is the same as 1/2 x squared minus 3/2. I wasn't going to write it, but if that's where they ended, I probably should show that one too. All the same thing. And then MS 73, yeah? 73 was the one that we did not get to do an example like yesterday. However, whenever you guys get to a homework problem, you don't have an exact example in your notes, where else should you be looking? Yeah. But this is still a complicated idea. Pause. For people that know English. Hopefully everyone. What does the word restrict mean? Contain. Contain? Yeah, I like that a little bit better. Because it's not that you're stopping it. You're just like holding it back, right? You're not really stopping it. You're more holding it back. So holding it back, guys, what's the normal domain of a squared function? Normal parabola. All real numbers. So if you're restricting, you're holding it back. You're only taking part of it. But which part? Okay, this whole paragraph, blah, blah, blah. What's it actually saying? Remember, the short and sweet version is what you guys are supposed to be writing down for your directions in your homework. You're trying to make the function one-to-one, right? Now, pause. What does one-to-one actually mean? Oh, so this is just explaining what that word is, which we already know. One-to-one is a function that has an inverse function. Then it says, okay, then find the inverse function, state the domains and ranges, explain. Okay. If we were to graph this guy, in section 1.7, the kid function, remember the kids? The kids are the transformations. What happens to my parabola right here? Right. Second? Ish. Should go all the way down. Does this fail the horizontal line test? With the domain of all whole numbers? Yes. But what was the point? Restricted. Hold it back. Restrict. So here's the deal. We can either restrict it by saying, let's take all the values greater than 2 that are equal to 2, or less than or equal to 2. Meaning, we can't have both branches. Think about the axis of symmetry and say, okay, either take the right or take the left. Technically, you could have taken either one. My advice would have been the right. Because I like keeping things as positive as possible instead of being negative. Just think, be optimistic. Go the greater than, not the less than sign. But technically, either one's okay. Because either one would have. If you cut off this branch, invertible. If you cut off that branch, invertible. So let's just go with my way if you guys don't mind. Domain only greater than or equal to 2. So how I restrict the domain is I think about the curve itself. Think about how it fails, and then take away the part. Take away half. Especially if it's symmetric. Take away one side of the symmetry so that it doesn't make a problem. Okay, he's restricted. Good. He's restricted to what? That. Does that pass the horizontal line test? Good. Now what? Oh, find the inverse. Got him. Switch x with y. But here's the dealio. If you start finding the inverse, aren't you going to have a plus or minus root x with a plus 2 equaling your y? That's technically wrong if we're only looking here. Do you guys know whether we would choose the plus or choose the minus to be this part? What do you guys think? If you choose the more positive, it'll be the plus. If you choose the more negative, it'll be a minus with a square root. You could also think if you were to graph this on a calculator, it would look like, which is exactly what I need. I don't want this one. That would be the minus. So if you graphed it, the 2 plus gives me the correct reflection. So for this restricted, I would need to keep the 2 plus root x. If you had chosen the other direction, less than, you would have needed to choose less than or equal to. You would have needed to choose the 2 minus. What was left? Say the domains and ranges. So I can look at him and I can say the domain of this dude was x greater than or equal to 2. I can look at him. How low does the original function go? 0. So then my range for him would be y greater than or equal to 0. For this guy, I haven't really done either. But wait, the really cool thing, why am I going to do this just super, super, super fast, not even looking at the graph? What did I just do? Switch it, right? The range steals from the domain, and the domain steals from the range. They switch. So I could have done that both ways. They're just saying there could be many answers because they're just leaving that possibility open for you could have chosen the minus instead, and if you had chosen the minus, you would have had to do that less than or equal to, so a few things would have changed, but we chose to go the positive direction because we're optimistic like that. Some of us. All right, cool kids. There we go. We're at the end of homework. Last call for questions. Going once, twice. Section 1.10. I got a meme for you. You ready? You guys relate? The title of today's section. The title of today's section is Math Models. Math Models? What does this have to do with anything? So because the title of the section wouldn't really tell you guys a lot, I figured I'd give you a meme. That's how we speak these days. Well, not me, you. Speak these days. That's not necessarily a dig. It's more of a sad, distorting reality. What's this section going to be about, guys? Math models. I don't know what that means, I don't think. Look at the meme. What's it going to be on? Word problems. Word problems. Now, good news for you. All right, focus in. I know I haven't shown you notes yet, but it's because I want you to think first. You might want to grab out your calculator. Ooh, that means some of homework. We get to use our calculators. Hey, go for it. Okay. Word problems are coming. A lot of kids, when they see a paragraph, maybe they're like this. They're like, they try and it just doesn't make sense. because they don't know how to organize the information, or they don't know what it's talking about, or they don't know how to change the English into math, how to translate. But to be honest, I think for most of you, it's not really like this. I mean, you read it and you're like, okay, I get it. Some people hate word problems because it doesn't make sense. Do you know the sadder reality though? For most of us? And I know it because I know which problems in homework, if I were to walk around and do a spot check every single day, instead of Google Classroom, and it was like semi-unofficial, and it's like, okay, you kind of have to have homework started, but it doesn't necessarily have to be done. I don't look at it in tons of depth. It's just really due by the end of the chapter when I really collect and look hard. I can almost guarantee which problem almost everyone would skip almost every time. Or two, or three. One. The NFL problem. Remember that one? Remember the NFL problem? The box being sent to the mail. Remember that one? There were problems. Not every time, but usually, isn't it like, okay, basic skills, words. What do we really do when we get to word problems? The majority of us, or at least of math students in general. You look at it and you're like, she'll tell me how to do it. Someone's going to ask on it. Right? So why? Hold on. I was grading quite a few of your homework, starting to until that Wi-Fi at Starbucks went out. I was grading a lot of your homeworks last night. Why am I writing comments like, even when stuck? You're allowed to be stuck on a homework problem, right? Even when stuck, even when confused, should still write directions and given information. What am I saying? Don't just get to a word problem and say, forget it. What am I seeing in your homework? There was something in homework 6 or 7, it was number 73 or 79 or something like that. And I was like, oh, blank, oh, blank, oh, blank. Oh, not even written there, hoping I don't realize blank. A lot of you guys are just getting to a word problem and being like, meh. So it's not even that you don't get it, it's that you're not even willing to read it. Because what are you supposed to do for every single word problem? Sorry, every single problem in homework. Yeah. But writing every single word? No. Writing down the important information. Your brains are supposed to be processing what's there and saying the short, sweet version is. And that's before you even start to solve. So all of you guys that are leaving those word problems totally blank, I'm going to keep taking off points. Why? Because you're being lazy, and I need you to get to a word problem and actually read it before you figure out or determine that you're stuck or not. Are we tracking? Okay, now it's not because I'm judging you because you're so much different than all the other years of math kids. You're all the same in some ways. Now some of you are trying the word problems, and some of you are actually writing down the given information, and some of you are actually solving it, like yourself, not just from Calc Chat. And there's a lot of in-betweens in there. But in this section, you can't just get to a word problem and stop, because guess what? You won't even start the entire section. So here's the nice thing. Do word problems get confusing? Yes. But is there still a way to read the words, or read the table, or read the graph, or read the equation, and not stay stuck? Now, do you guys necessarily need to write down, I'm going to have words and tables and graphs and equations? No, you can write it down if you want. We've already talked about that. There are going to be words, there are going to be numbers, aka tables, aka points. There are going to be graphs, there's going to be algebra. Wait, where have we seen tables this year? In the class. And specifically, which one? That one, right? Okay. So, John Yoon, how well do you think you know the kids in this class? Pretty good? Half the names? Okay, we'll see. I know you know this one. And this one best. Each of them should have a stack of free papers. If you don't know someone, if someone you trust to be like, hey, who's this kid? Okay, actually, I have a season check. That makes life easier. You guys are going to get your Precalc graphing calculator handbooks back because do you guys see what's happening right underneath the different forms of math that you can see? Line of best fit. These squares. What's the next word? Regression. Hey, what am I going back to? Kimmy's gone. Why am I having John get back your Precalc graphing calculator handbook stuff?
We're probably going to need
Calculator worksheet. Number 2 is where homework starts. All the way up through number 18. And I don't think I give you very many. I'm going to give you 1 or 2 just to review. But calculator worksheet number 2 is where homework starts. The nice thing is, guys, I don't need to teach that to you. Now, there's some new wording, like the line of best fit or the least squares regression line. But, guys, long story short, if you see line and you see regression, which regression are you running? The linear. No big deal. There's some new terminology. Some of you guys were asking me once upon a time what the R is for. Put a big old parenthesis. You don't need to memorize it. It's basically telling us how closely the regression line hits the data, how far off it is, how precise it is. But we're not a stats class. We're not going to stress too much about it. We're just getting the idea of we have these lists, we put in data, we can get an equation from the programming with the regression line. We can use it. Guys, it's all calculator worksheet number 2 stuff. So you're getting back your handbook, you're getting back your calculator worksheets. That way you can use it if you need to review. Okay? So homework starts where we've already been. There's going to be word problems. But you know how to do them. There's even a question, I think one of your homework problems that says, interpret the slope. Calculator worksheet number 7C. You didn't like it then, but we talked about it. Can you use it to do it this time at home? Okay. So to some degree. I hope it's not as scary because you've already seen some of it. We've already struggled through some of it. Okay? But then after calculator worksheet stuff. Then, to be honest, I'm going to freeze the screen because some of you guys I see are still writing. Hopefully not in a super stressful way because I'm telling you pretty much whatever you need for those first few problems is totally in your graphing calculator handbook. So it's not really that you have to stress too much besides the fact when you see linear regression or least squares regression line, you know it's just linear regression. But can I show you the beginning of homework real quick? And get up to where the rest of homework goes after this. Okay, we have vocab. A lot of vocab. You guys know the vocab's in the section, right? Bold words, go look for them. Okay, now what do you see? Okay, but wait. These are tables, right? With X's and Y's? And I bet they're not going to want us to actually use 1998. I bet they're going to want us to use, like, I don't know, 8 and 9 and 10. Oh yeah, 8 and 9 and 10, years from. Or down here, they're not going to necessarily want us to use 1920, but maybe 20. Okay, good. All things we've talked about. Tables, yeah. Regressions, yeah. Graphing one on top of a scatter plot, yeah. Interpret the slope. Okay, calculator worksheet number 2. But after number 18, oh, it actually gets easier. Doesn't it look easier? No? Well, there's no more paragraphs. Oh, gosh, you guys like the paragraphs. Okay, that's weird. It's a lot shorter. But what do you see in the directions? Because some of you would just go here and say, where? Okay, you're supposed to read the directions and summarize them every time. How would you guys summarize this paragraph? Read it real quick. Take a second. Read the paragraph. What's the short sweep of this paragraph? Okay, so this is the goal, right? That's the goal. Linear model that relates y and x. We're supposed to make our own equation? Oh, wait. What was up here? Clue words. Do you guys see down here there's more clue words? Direct variation. What's down here? Inverse variation. I think we need to go talk about what this direct variation, directly proportional, inverse variation, inversely proportional. I think we need to figure out what that is. And maybe once we figure that out, we'll be good to go. Ready? Oh, that's cheating. That's okay. You should ask Kyle how he cheated. He totally held it upside down and he was like, yay, it's so cheating. Anyway, coming back. Do it the right way. It's more fun. Anyway, back to notes. Because I'm losing people to games. That's not a good thing. That's not us. Yes, it is. After the review stuff, right? Now we have translating. Here's a long story short, guys. We have four translating things to go through. And then we're golden. But in homework, you guys have to, after the tables, you have to read the paragraph directions. And it's silly that I'm telling you that, because you're supposed to be literally summarizing them in your homework anyway. How can you summarize if you don't read them? Awkward people that are missing points in all their homeworks because they're not writing directions. Anyway, you're going to have to read the paragraphs because it's going to tell you what to do. But the nice thing is, didn't we just see that whole directly proportional or direct variation thing a second ago in like 2 or 3 different sections of homework? What does it mean? It means, with direct variation, whatever's before the wording goes in the Y spot. Whatever's after the wording goes in the X spot with a little constant of proportionality K being multiplied. Direct variation, directly proportional to. Directly varying to. Varies directly. Just means there's an equation with a constant, and y equals that constant times x. The only thing that's going to change as you guys start doing actual word problems or reading paragraphs. Sometimes you can just use y and x, no big deal. But sometimes you're going to have to use other variables, like, I don't know, in money, interest is usually a capital I. Amount of the investment is usually a capital P. Anybody remember why the initial amount of an investment or the initial balance of an account is called P? Oh, Dylan, you were just whispering it?
What?
You're saying he. There's a lot of he's back there. Anyway. Yeah, principal. Good job, Dylan. And whoever you heard it from, whoever else said it. Principal. The principal is the initial amount of anything with money. Almost always. Principal. Oh, wait a minute. So, how do we translate that into math? Simple interest is directly proportional to the amount of the investment. Math models means make an equation that models the math. Oh. Okay. So can't we just say I equals K times P? That's it? That's it. Really? That's all that's going on in homework? You just make little baby equations? Well, part of homework. Can we go back to homework real fast? Is that all it's saying is just translate? Well, we are supposed to find a model, but hold on. Uh-oh, what was the part that was before that whole finding the model thing? Use the givens. So as soon as we see directly proportional to, we can say, yay, y equals k times x. What does it mean by use the givens? Like in number 19, how would you use the givens? Plug in 14 for y, plug in 2 for x, and solve for k. And if you solve for k, isn't that the same thing as slope? Y equals mx plus b? So couldn't you just say 14 divided by 2 is 7, so my final model is y equals 7x? Dun, 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 dun. Really? So sometimes we're just translating, and sometimes they give us clues and we can actually find who k is. But for right now, we're just translating, and so we're just leaving it with k. So how would you guys set up the model? The general model, the k, we don't know who he is. There are no numbers to find it. What's the model for this statement? Can't use y, can't use x. They give us variables. Or 2 variables, or a baby equation with a question. What's on the left side of the equals?
S.
Give them a second to process. Who is S? Oh, the distance an object falls, of course. Whatever. So all of that wording just got dealt with, right? What comes after that wording? What does that mean?
Direct
K times. We have the Y, in this case the S on one side, equals K times because of the direct variation, and then what comes next?
T.
Nope. See it? Who is T? Oh, the duration of the fall, of course. Okay, cool. But there we go. Dun, dun, dun. Dun, dun. With a square. But you guys get the idea, or else you wouldn't have said K times T. Independent variable on the left side, dependent variable, direct variation is being multiplied by some K. Which K? I don't know. If they give you clues, go find them by plugging in. If they don't, say okay. Huh, okay. Anyway. Inverse. Who's that? That was the next section. Inverse. Same wording, got guys on the left. Independent variables, sorry, are on the right. Dependent variables are on the left. Of course, the variables can change names, but what's different is now we're doing K over. What's different is now we're doing K over. K divided by. I'll do a real world example in just a second, but I'll give you a second to process, put it down. Varies inversely. Inverse variation. Inversely proportional to. Use a Starbucks example in just 1 second. Inverse variation in the real world, direct variation in the real world. You guys made an equation out of the example? Bust it out, you got it. Demand for a product varies inversely as the price of the product. Well, it does. What does inverse mean? Awkward. Demand varies inversely as the price of the product. Think about it in real world terms. I know you're not a senior yet, most of you. I know not most of you are in econ. None of you are in econ. That's second semester, senior year. But demand and price, how do those go together? Does anybody know the housing market? Demand and price. How about oil? We're looking at Yemen on Saudi Arabia, right?
Yes.
Like 5.7 million barrels a day. Demand and price. Summertime gas prices. Demand and price. As demand goes,
Prices goes up.
the demand for a product varies inversely as the price of a product. Now, here's the interesting thing. We just said as demand goes. You just made demand the independent or the dependent? Not in our example. We said as demand. He was the guy moving and price was being affected. We did it the wrong way. Check it. Where's demand in this problem? It's on the first side. He's the, what are Y's? Independent or dependent? Dependent. Remember? F of X, he's the guy dependent on the independent variable, the X. Okay, so hold on. Let's reword our statement. As price goes up, demand goes down. What do you think sales are for? Right? As price goes up, people are like, oh, I don't want to pay that. Now, there are some luxury items, yes, where it's like, well, because the price is. But there had to be a reason for that first. Someone doesn't just come into the market and say, I'm going to charge a load of money and then you are going to want it. No, that's not how it works. So let's do it this way. As price goes down, people want it more, right? Now, there's economics, that there's tricky things to all of that. But what this is saying, inverse relationship, as the price goes down, the demand goes up. As the price goes up, the demand goes up. So in the summer, gas prices, what always happens? The price goes up. Why are they doing that? People are traveling. They have to buy gas. But as the price goes up, don't people start kind of watching how much gas they're using? Right? Frappy hour at Starbucks. That wasn't my example. I'm going to use my Starbucks example in a second. But frappy hour at Starbucks, why do all the Starbucks baristas say, it's like the worst time of day, it's like the worst time of the year. Why are they all just kind of stressed out during frappy hour?
There's all the crazy coffee people.
It's buy one, get one free. The drive-through lines are crazy. Everyone's hot. Everyone wants their buy one, get one free frappuccinos, and the poor baristas are like, in the back, trying to make it all. Right? Why? Because the price goes down, demand goes up. So what's going on with inverse versus direct variation? The easy way to describe these guys, I mean, mathematically, it's times versus divide. It's multiplication, direct across, and then division. But the big idea is direct variation as our independent variable, x goes up, y goes up. And similarly, vice versa, as x goes down, y goes down. Inverse variation is as x goes up, y goes down. So my Starbucks example, beyond frappy hours, is temperature. What if the independent variable was temperature? What if the independent variable is temperature? Temperature outside and the demand for. Why is the demand for? Okay, which kind of variation would be as the temperature goes up or down? Hold on, temperature related to iced drinks. Which variation? Direct or inverse? Temperature and a demand for iced drinks. Blended drinks, iced drinks, cold drinks. Direct? So as temperature goes up, it's hotter, demand goes up for ice drinks normally, right? Okay, so direct variation. So what Starbucks example along the same lines would be inverse? Temperature and hot drinks. Does that make sense? Temperature and hot drinks, demand for hot drinks. As temperature goes up, demand for hot drinks go down. That's what my mom always wants her coffee hot. She says it lasts longer because the ice drinks she sips it too fast. But anyway, whatever. She loves her hot coffee even with 92 degrees outside. But coming back, for most people, temperature goes up, demand for hot drinks go down, and temperature goes up, demand for hot ice drinks goes up. Anyway, long story short, just like a broad what's going on, direct versus inverse, no big deal, right? But we have two more variations, and guys, the crazy thing is they're not new. They're going to be different ways of putting together this direct inverse thing. So it's not so much that there's some extra. Now, there's lots of ways variables can be related. But in this section, pretty much direct or inverse or some, sticky now, some combination of the two or some joint variation. Okay, I'm just reading the words. Let's figure out what they say. Sorry, that's not the next one. Some combination, combined variation, some combination of the two. Oh, literally. Combination means combined. Next paragraph, it looks nasty. We're going to break it down. Some combination of the two. So this paragraph somehow has a combination of both direct and inverse, and we need to make one model, one equation that has it all there. Oh, they don't even give us variables. So we get to choose our own, but maybe in a way that we're being somewhat mathematically informed. Like, I'm pretty sure length should be L. You guys good with that? Pretty sure cross-sectional area should be A. And why not? Let's call resistance. Sounds good to me. Okay. So resistance of the copper wire. resistance of a copper wire carrying electrical current is directly proportional to its length and, I get the combined variation. Look, it has both, right? Some of you would make this way harder than it has to be. What's on the left, or what's dependent in this entire problem before any of this wording comes? Who's on the left of my equation? R. All of that jazz. Resistance of a copper wire carrying electrical current. R is directly proportional to length. How would you guys just do that statement? Directly proportional to length. KL. Here's where some people get confused. And at the same time, inversely proportional to cross-sectional area.
Over A.
It's as easy as that. At the same time, K can be times L and K can be over A. Directly to L, inversely to A. Guys, we've just been practicing translating, but once again, in homework, if they start giving us clues, what are we going to start doing to the clues? Plugging into the model, finding the K, and then if they want us to, using it. Hey, like the regressions. In calculator worksheet number 2, didn't you sometimes find an equation and then use it in another part? Yes. Same thing here. So maybe you're going to have to form the model first, not with your calculator like the beginning, but actually form the model yourself, use the model to get it nice and precise, and then, or I should say use the givens to make it exact, and then use the model to do something. So it's not that crazy. The instructions aren't going to be that crazy, but let's make sure you can still translate. That was combined. One last variation. One last one. Joint variation. Jointly just means whatever variation you're doing, it's directly or inversely related to more than one variable at the same time. So it's kind of like directly related to 2 variables or 3 variables, inversely related to 2 variables or 3 variables. So if you guys notice, for this one, they're just using the direct variation model. And I think on ours it's all direct variation. But jointly, it's dependent is equal to K times, it's dependent on multiple things.
Wait, Z varies jointly as X and Y. What?
So it's the 2 variables at once, you see it? So that jointly is you have like a direct variation, but it's 2 variables at once. So down here when we're reading, kinetic energy of an object, E, varies jointly. I know automatically there's more than one variable coming. Mass is going to be 1, and the square of the velocity is going to be the other one. So when I come down here to make my equation, E equals?
K on V. Squared.
Okay. The square of the object's velocity. So jointly just says, hey, you're looking for more than one. Just keep an eye open on the and. And as always, keep an eye open for any mathematical terms that might fit in as far as the squared or the root or the cubed or whatever other quantity. So guys, yeah, this is a section all on word problems, but the dealio is they're very specific types of word problems. First of all, tables and regression lines, no big deal, been there. And second of all, basically taking wording and trying to put it together into equations. Sometimes given clues and we plug it in. Sometimes being asked to go one step beyond that and to actually use it. So if I was to put up on the board maybe a couple examples like homework, if I was, and if we were to have tons of time, what would they want you to do in something given clues? Yeah, not just make the model, but then take your clues and plug it in, right? But then this one just says to solve. So we would be done once we would get down to y is equal to 2 pi x. We're like, yeah, let's solve the model, no big deal. How about this one? Same thing, there are clues, except in this one we have to figure out, does it look like as x's go up, y's go up? Does it look like x is going up and y is going down? But once we figure out which one seems to make sense, aren't we going to plug it in, and plug it in, and solve? And pretty quickly maybe we could figure out what's going on is we have a rise over run of 2 over 5. But still, we're stopping. But what's going to happen if we... Oh, same thing. Homework then. A lot of translating and plugging in. Sound good? Alright, don't get scared of the word problems. You guys got this. Homework due tomorrow? See you later. Write the directions, but summarize.
Oh no.
Play harder on yourself. Cut it down. Short and sweet.